So I'm in the pool store waiting for a gasket that they said they had in the store, but they had to go a different location, so I'm sitting in there. And I know that I'm paying $35 or something, and it was $5, they always up the price. In comes a individual asking about pool chemicals. And so he says, I just tested the pH of my water, and the pH was too high. And I'm just thinking to myself, oh, it's basic, you know? And I think I said it out loud, oh, your pool is too basic. And then the pool person chimed in and said, no, you just need pH, you need pH down. And I was like, yeah, because it's too basic. No, they need the pH down. I'm like, okay, whatever, all right? And so I'm sitting in there and waiting, and he comes back about 20 minutes later, and he says, okay, my pool is now too low in pH. Oh, so I said to myself, and I said it out loud again, well, it's too acidic now. No, you need to pH up. And he bought this chemical. And before I left, guess what he came back to buy more of? He kept adding too much, and there's a reason for that. And we're going to learn about that in when you neutralize. But he was trying to neutralize an original what? Basic pool with adding some acid to bring it down. And then when he brought it down too much, he wanted to raise the pH. In any case, the funny thing is, it's not that funny, but he was paying for these chemicals. Now, I'm a label guy. I like to look at labels. I always like to say what's in things. You're like, hey, this says pH up, and people will just pour it. What are you using right there? We're using pH up. But if you look at the label, it's sodium carbonate. And what the heck is sodium carbonate? Well, sodium carbonate is Na2CO3, and everyone knows that because I wrote that there. Okay. But what does it break apart? Well, sodium is always soluble, so we have 2 sodium ions, and we've got this carbonate that's CO3 negative 2. Okay, great stuff there, Grotsky, I see that. What's the big deal? Well, CO3 negative 2 can ionize water. I'm going to use a new way to describe. Well, what do we know about CO3? CO3, even though it's 4 atoms, is negative 2, has a high charge. And when you drop sodium carbonate, or, pH up into a pool to raise the pH from an acidic to maybe neutral, we know it's sitting around water. And so what I have to say is that CO3 negative 2 can ionize water. Same thing as saying that it can do this. Pull an H from the water. This becomes HCO3 negative. It's called a bicarb ion. What does the water become by losing an H plus? That's right, hydroxide, as you guys told me telepathically. Okay, that's how we're working today. Evan, why would you say that about me telepathically? Oh my God, I didn't know it. You think I'm gaining weight? Oh my God. All right. Okay, it's getting weird now. Okay, stop. Any case, so this is acting as a what? As it's giving an H plus. Acting as an acid, maybe? This is accepting an H plus, a base. The result is that CO3 negative 2, this part of the salt, is basic. It's basic. Oh my gosh, I dropped sodium carbonate in water. It dissociates into these aqueous ions. We all know sodium plus is a spectator, and it's this ion, it ionizes water, and makes hydroxides. And we know by adding hydroxides, the pH is going to rise. So pH up is just sodium carbonate. Now, if you buy pH up in the store, you pay 10 times what it is in Stop and Shop or King Cullen or any other. Sodium carbonate is washing soda. It's about $1 per pound. Here it's about $10 per pound because they put in a fancy label and it's a special pool chemical. It's sodium carbonate. It's washing soda. Okay? And so it works the same way whether you use it as a soap or you use it to bring the pH up. Why do we use it as a soap for washing? Because we know that what? Hydroxides can break bonds. They can break the grime and the grease. That's why we use it, okay, as a soap. All right, so that's a basic salt. So you should be able to recognize whether salts are basic, acidic, or neutral. Now, when I say salt, I mean that there's what? Sodium plus, a CO3 negative 2, and it beat goes on. But when this dissolves in water, and we should know why it dissolves, because it's soluble, all things we have discussed. So this has an ion that can react with water, okay? What about pH down? Poor guy came in, kept buying the same stuff as his pH went 2 up, okay? He bought too much of this and it kept going up and down all day, okay? Now, what about pH down? Well, this says, okay, sodium bisulfate, all right? So sodium bisulfate is NaHSO4. And in water, this is going to dissolve. How do I know? A group 1 ion is always soluble. So this is going to make my Na plus and my HSO4 negative. Question is, what does the Na plus do in water? Rhymes with spectates exactly.
Wow, I wonder what it is.
Spectates, if you're a rapper like me. So it's going to spectate, not do anything. Okay, but what does this guy do? And this got to go. Okay, felt like I was close. Okay, what does this guy do? Okay, well, let's see. HSO4, negative 1, sitting in water. And the reason why I write it in water is because when I dissolve them, there's going to be so much water it's in contact with, right? So what's going to happen? That's the question. Well, what do we know? It's a pH down chemical. So how do you think this is going to react if it's going to lower the pH? Is it going to produce OH minuses, or is it going to produce H3O pluses? H3O pluses. Okay, but why do we know that? And how do I figure that out? Okay, well, let me ask you something. If you're a strong acid, what if I was to add this into the pool? HCl plus the water in the pool. What am I going to make? Isn't this strong acid going to protonate this water? And it is not going to make H3O plus? And what remains is Cl negative. Now that's a strong acid. It has what kind of Ka? Large or small?
Large.
Very large. Good job. That means tremendously it goes forward. Tremendously. In fact, we would see the reaction goes to completion. Let me ask you a question. Why is this a completion reaction? Why are strong acids strong bases? And by the way, this is not a strong base. Okay? This is not going to be a strong acid. So there's going to be some equilibrium here. But it does go enough forward to make enough of this, in this case, to raise the pH. But in this case, the arrow doesn't go back. Why do strong acids go completely forward? Let's go to our table of fun. Strong acids have Kas that are extremely large because they produce what? Kas are products of reactants. If you're a strong acid, every single HI dissociates. So you have tremendously high HIs. Okay? High, okay, but no, they break apart into H plus and I negative. The reason why a strong acid is a strong acid is that the conjugate base that remains has no ability to grab an H plus to reform the acid. In fact, this is a lie. These guys don't act as bases. Fake news, nah. Fake bases. They don't do anything. They have no ability. They spectate. Cl does what? Spectates. So the reason why hydrochloric acid doesn't or goes forward is because there is zero ability in the conjugate base to grab an H plus. And you could say to yourself, well, why is that, Mr. Grodsky? Oh, iodine is a big atom. Look, it's at N equals 5, right? It's low. And what? It's -1. Its radius is big. Coulomb's law, low charge. So these guys are big ions. Remember, they get bigger as they become negative, and they're spreading that -1 over a big area. These guys can attract them. Hey, NO3, that spectates. That's 4 atoms with a -1. And oh, look at this, HSO4 negative. That's the conjugate base of this strong acid. Let's think about this for a second. That's the answer here for this next one. Why does pH down, which has this ion in its salt, why does it bring the pH down? Well, hello, HSO4 has an H, okay? But couldn't it accept an H plus? This guy's -1, so couldn't it accept an H plus? Or lose an H plus? That's the confusing part. Hold on. H2SO4 is a strong acid. Its conjugate base is HO4 negative. What does that mean? Why is H2SO4 sulfuric acid a strong acid? Its conjugate base has no ability to grab an H plus. The conjugate base has no ability to reform the acid. Its conjugate base has no ability to be a base. So this can't be a base. In fact, if you go find HSO4 negative, there it is. And what is it? A weak acid. One of the stronger weak acids, but still a weak acid. So this is going to give off H pluses. So what does this do? It gives off an H plus to the water. What does water become? H3O plus. And of course what remains is SO4 -2. All right, and by the way, party people, H3O plus is synonymous with H plus, and that's how that salt is an acidic salt, okay? Let me ask you a question. If I was to tell that person, hey, drop NaCl into the pool, would that help his pH problem? Would that help his pH problem? If I said, hey, drop NaCl. Remember, these are just salts that have a negative ion that can accept H's. This is a salt that gives off an H. So if I give you NaCl, will that change the pH? Anybody? Will that change the pH? Anyone?
Yes.
Well, what does NaCl break apart into? Na plus, hey, that's a spectator, group 1 ion. And what? Another spectator. Chlorine doesn't do anything to water. Okay? Notice the reactions, guys. I have them sitting in water. And they are either making a hydroxide or they're going to make that H3O plus. So NaCl is going to break into an Na plus that spectates and a conjugate base of a strong acid that just spectates. It's a neutral salt. Okay? Something to think about as we go forward. All right? All right, moving on. I want to revisit a reaction we did, or at least we were going to do, but because of our code rules we didn't. Hey, we blew up the pumpkin digitally. Okay, it wasn't as fun as we would do as we would normally go outside. But the reaction was acetylene plus oxygen, CO2, and water, combustion. This is a redox reaction. But to make the acetylene gas, because I'm not supposed to have a tank, so you just make it, here was the reaction. I dropped solid calcium carbide into water. I made acetylene and I made this milky white substance, lime water. Okay? Lime. All right? What kind of reaction is this? Now I showed you the mechanism. What kind of reaction is this? I dropped calcium carbide. Think with me. Calcium carbide in water. It dissolves. What do you think it dissolves into? Calcium plus, and then C2, -2. Oh, -2. -2. What is the carbide ion doing? Isn't it yanking H's from water? The carbide ion is ionizing water. It's got this negative end, and it's pulling the H's. And if you're in what? An H plus ion acceptor, a proton acceptor, you're called a what? base or an acid? Base. The water is acting as an acid, donating the proton. The carbide ion is acting as a base and accepting them. So as we pull the H's from, we make what? Hydroxides. This, my friends, this reaction of dropping water onto calcium carbide and getting the fizzing, and by the way, I did this in the what? I did this actually live with the ice cubes and water, and then I lit it, okay? That, my friends, is a acid-base reaction. Also, it's acid-base because isn't this donating a pair of electrons? So bases are proton acceptors or electron pair donators. And this is an acid because this water is what? Accepting a pair of electrons. Both definitions you have to know. All right? All right, good times. So let's go to the new worksheet. We had some work last night, and I want to start modeling some of these stoich problems. So we're going to take out that worksheet, okay, and do some work together. All right. So let's go there. Okay, and last night you guys were writing net ion reactions. We'll get back to that. And last night you were solving, hey, how much of something else do you need to neutralize? This word neutralize we're going to spend more time working on, okay? But I do want to make one important point. We talk about neutralizing, okay? And I will do that with the worksheet. This homework, I walked you through the video. I don't want to spend time on something I've already done. So I'm going to go to, not this one, yeah, this one, okay? So we're going to start this worksheet together, which is our homework, all right? Okay, so this is our homework, and I want to start modeling some problems, all right? Right, okay. So I'm going to take this off, but this little mini lesson was about understanding that salts can be acid or basic depending upon the components that dissociate. All right, so we should know the following when we're doing this. Things that we hold tight to our vest when we're doing acid-base problems are these basics. Hey, water breaks apart naturally into H+, sometimes we call it H3O+, okay? And of course it breaks apart into hydroxide ions. It's a 1-to-1. Now, it doesn't do it very much. So this is a liquid, this is aqueous, this is aqueous. So when we do a law of mass action, or that formula that helps us get KQ, we do products over reactants. Here's my products. These brackets are the molar concentrations. Divide by the reactants, but hey, solids and liquids do not apply. Products over reactants, coefficients become exponents. These all are 1 in front, so they become 1, but I don't write that there. And we do what? Products over reactants. Solids and liquids do not apply. We can't put a liquid here because it doesn't have a molarity. And this, of course, equals our KQ, but we call this KW for water. And we have measured this value to be 10 to negative 14. Okay. Now, the combination of these two values has to always equal this value. If I add a base, this number is going to be bigger, and this number is going to be smaller, and vice versa. That's what the first question's about. Okay, we're going to add a base. All right? And so we're going to increase this concentration, which means this number has to get smaller for this to be the same. Okay, now, something else to keep close to our vest is that we understand that there's a negative log here, and I'll should do this in the color to keep it pretty. All right, I don't know where my colors are. So we've got this as a negative log, gives me the pH. Sorry, bad Grotsky. Little p means negative log. And why is it H? Because it's of the H+ ion concentration. We like to do negative log of the hydroxide. That gives me the POH. And if I do the what? Negative log of this number, we call that the pKw. Okay, what do we know? These two values equal together equals the pKw, which of course is 14. Why? Because the convention that we use for pH to try to understand that huge range of possibilities of concentrations of H3O plus and OH minus, we want to stuff that into a single exponent. Log means take this small number, and it can be extremely small, and do what with it? Stuff it into an exponent. Also understand, if I start you with a pH, to go back into the actual number, to convert your what? Your exponent back, we do 10 to the negative x. Really important to understand that diagram. Okay, so let's go do the problem. All right, and this is now getting into acid-base titration. Titration is a technique we're going to spend a lot of time on, but it's a technique that involves neutralization. I'll talk about that in a second. But in any case, let's get to the problem. What is the initial pH of a solution? Okay, so tell me what I want. Made from 5 grams of calcium hydroxide, dissolved in 2.8 liters of water. Okay, first thing I have to do is identify what my chemical is. All right, calcium hydroxide. What is that? Is that a neutral salt, or a salt that's basic, or a salt that's acidic, acid base, strong acid, strong base? What is calcium hydroxide? It's a base, it's a strong base. Anytime you have a group 1 or group 2 ion with a hydroxide, very soluble. Okay, now in terms of the group 2 ions, they're strong base, completely dissociate, but under low concentrations, something we'll talk about another time. But we're going to see what the initial pH of the solution is. So when you have a multi-step problem like this, I always tell my students, and you guys are my students, I say, don't ask what you do first, ask what you do last. So I'm looking for the what? Initial pH of the solution. Now, if I'm looking for the pH, what is going to get me the pH? What do I need? What's the last step? What would be the last step? Not what you do first, it's what you do last that's going to help you set up these problems. If I'm looking for a pH, how do I get a pH? Well, I can either what? Take the negative log of my H plus or H3O plus concentration, correct? Or I can do what? Get a POH, subtract 14 to get a pH, correct? So somehow, some way, I'm either dealing with a concentration here or a concentration here. Since they're giving me the base, okay, to be calcium hydroxide, I'm going to know that I'm dealing with a hydroxide concentration. So my plan of action is, hey, let's go find this number here. That bracket is a molarity. And I can do it 2 ways, and I want to talk about the 2 ways I can do it before we actually do it. Here's way number 1. And you don't have to do it the way that I do. What do I know? Kw equals the what? Product of the H plus times the OH minus. Now, we know we want the pH, so we've got to solve for H plus in this case. Now I know what this number is. 10 to negative 14. Okay, we're going to solve for this number, right? By doing the math. I'm going to solve for H plus. So algebraically, I would take 10 to the negative 14 and divide by the molarity that I get from using the 5 grams, convert to moles, divide by liters, get molarity of hydroxide, and I can solve for the H plus. Once I have the H plus, I can do negative log to get my pH. I'm not a big fan of that method, but all I'm doing is what? Once I find this value, I know this number, I can solve for this value, and then do negative log. Here's the second way. This is the one I like. Hey, I'm going to get the molarity of my hydroxide, moles over liter. That's pretty simple. And then I'm going to take a negative log of it directly to get a POH. and subtract from 14. I'm loving that. So I'm going to get this value, molarity, brackets is molarity, negative log it, I love pH, POH. Negative log of the OH is POH. I know plus some number equals 14, so subtract from 14. So get the hydroxide concentration. I'm going to negative log it. And I'm going to do 14 minus that will give my pH. Either way, you get the same answer. I don't care which way you go. I prefer number 2, but that's just me being told. So, what do we do last? The last thing for me is that we can either get a what? Negative log of an H plus, or I can subtract from 14. Bottom line is, I need a molarity of my hydroxide. I need this value. That's what that means. So, to get my molarity, what is molarity? Molarity is equal to the mole over the liter of solution. Well, party people, they gave me the liters, and they gave me the grams. So I need to solve for moles of my base. So given 5 grams of calcium hydroxide, I'm going to convert this how heavy number into a how many number, because I need to know how many of them. And I believe calcium is 40. I'm doing a formula mass because I want to get rid of grams. I'm cool, I don't write the E, 1 mole. And so, calcium is 40. 2 times 16 is 32 plus 4. I get 76. No, 2 times 2 is 2. 74. And all I'm doing there, party people, is getting moles of calcium hydroxide. Now, don't lose sight that what are we after? The molarity of the hydroxide, not just the molarity of the calcium hydroxide. We want the hydroxide ions. That's what we're after. That's what's happening in water. The calcium hydroxide is not part of what's water, it's the hydroxide. So I'm going to do one more stoichiometry thing here. I'm going to get rid of calcium hydroxide, and some people can see this without doing it. And for every one of these, how many hydroxides are there? For every 1 calcium hydroxide, how many hydroxides? 2. Important. And that's going to give me what? Moles of OH minus. I'm not liking green. Now, I'll divide that by the liters, which is 2.80. That'll give me my concentration of my hydroxide. So, take my handy dandy calculator. Okay. 5 divided by 74 times 2, and I get for this number right here, I get, do it in green to keep it same, 0.135. I'm going to divide that, that's moles now, it's the moles of hydroxide, so divide by 2.80, and I get the concentration of my hydroxide to be 0.04826. That's the concentration of my hydroxide. What do I do with that? I am looking for a pH. I could put it where? Here and divide by it and solve for the H plus, then do negative log, but I love to do a what? POH. So negative log it. That's what the little p means. So negative log, second answer, and I get 1.316. People will put this as the answer because they don't understand that is not the p. It's not the pH. Little p of OH. It's the hydroxide. They didn't ask for POH, but understanding what POH is helps me get to the pH. So how do I answer this? Well, what do I know? I know that 14, which is the pKw, equals the pH plus the POH. So if the POH is 1.36, I subtract that from 14. And of course, what I get a pH to be 12.7. which makes sense to me. That's a strong base. I should have a pH above 7. Now, could you have done that a different way? Well, let's see if it gives me the same answer. Of course it will. What was the value of the H plus? So I'm going to divide second function, 10 to negative x, negative 14. I'm going to divide that by, what was my concentration? Oh, 0.04826. Okay, that gives me 2.07 times 10 negative 13. I'm going to do negative log of that. Second answer. And I get 12.68. That rounds to 12.7. All right, one little point here before I'm done. What's this problem about? Neutralizing. I want to neutralize all this base that I added. So how many moles of hydroxides do I have in the solution? How many moles of H pluses do I need to get rid of all of the OH minuses? The same number, correct? Why? Is water good going this way? What's the KW? Tiny. It's terrible going that way. It only goes forward a little bit. A small equilibrium constant means that there's more what? More reactants favored. So if you're bad going this way, what are you good going in reverse? Incredibly good. So every H plus that sees a hydroxide is going to make water. That's neutralization. And I'm going to bring this down to 7, hopefully. Have a great day. Have a good day off, too.